In this lesson, we're going to talk about antiderivatives. So be sure to set your paper up for Cornell Notes with your essential question and lesson objective. Okay? And we're going to, by the end of this lesson, understand the relationship between derivatives and antiderivatives. And you will also need to be able to recognize the antiderivative of some basic functions. So let's start with an antiderivative. What we've done up until this point is we've been given a function and we've taken its derivative. Okay, now we're going to turn things around and work backwards. So instead of giving you the function, I'm going to give you the derivative and ask you to figure out what the original function was. So that process of working backwards from a derivative to the function is called the antiderivative. Okay. An antiderivative is also called an integral. So if we say take the integral or find the antiderivative, that is the same thing. Okay. So in the notation here, we've got the integral of little f dx is equal to capital F dx, or capital F of x plus c. The c is a constant, and the capital F would be the antiderivative of little f. Another way that might make a little more sense to you is if I said the integral of f prime of x, which is the derivative of f of x, when I take the integral of f prime, I get back to my original function, which would be f of x. The plus c we'll discuss in a minute. It just stands for a constant or a number that does not have a variable. Integration is the inverse operation of differentiation. So if I have an equation with a derivative in it and I need to get back to the original, I use the inverse. Just like when you're solving equations, if you had x plus 2 equals something and I needed to get the x isolated, then I would use subtraction because subtraction and addition are inverse operations. Well, integration and differentiation work the same way. They are inverses of each other. Okay, here are some basic integration rules. We start with the differentiation rules that we already know on the left side and show you how working backwards you get an integration formula. So if you will stop the video and write those down, then we will look at some examples. Okay, so a few examples. Let's look at example number 1. And in example number 1, I have addition and subtraction. So according to the rules that we just copied down, instead of trying to take one big antiderivative, I can split this up into 3 integrals. So this would be the integral of x squared dx minus the integral of 3x, but the 3, since it's a constant, can move to the front and just multiply times the integral of x. And then I'm going to add the integral of 4, which is a constant by itself. Okay, now one of the main rules you're going to need to remember is the rule for how to integrate x to a power. Okay, so according to the rules that you wrote down earlier, we're going to add 1 to the exponent and divide by that new power. Remember when we took derivatives, we multiplied times the power and subtracted 1. Well, if integrals are the inverse operation, instead of multiplying and subtracting, then we need to be adding and dividing, which is exactly what the rule says. So instead of x squared, we're going to add 1 to the power, and we're going to get x cubed divided by our new exponent, which is 3. Okay, minus 3 times the integral of x. Well, the exponent on an x is just a 1, so we're going to follow our rule again. We're going to add 1 to the power and divide by the new power, so x squared over 2. And then we're going to, on a constant, just put an x back in with it, because if I took the derivative of 4x, I would just get 4, but I'm working backwards right now. Okay, so, and then don't forget, on all integral problems that are called, these are called indefinite integrals. On all indefinite integrals, you need to add in a constant, because there could be a number added to that when I took the derivative of a constant is 0. Okay, so all constants would end up dropping out of the derivative. Well, when I'm integrating back, I need to recognize the fact that there could have been a number there. And later on, we'll talk about how to find out what that number is or if there was a number for certain problems. Okay, now let's try number 2. Again, we've got x to a power. So we're going to use the rule that says we're going to add 1 to the power. So negative 5 plus 1 would give me x to the negative 4. And then I divide by my new power, which is negative 4, and I add the constant. Now, on this one, you could simplify because the x is a negative exponent, so I could rewrite that to say negative 1 over 4x to the fourth. Remember, the negative power moves the variable down to the bottom of the fraction, and then the negative on the 4 in the denominator I just put in the front. Okay, and I still need my plus c. Okay, on the last one, this is just a constant. Anytime you're integrating just a constant, you're going to put an x back with it because the derivative of 9x is 9, so the integral of 9 is 9x. And don't forget plus c, because there could have been a constant with that when we took its derivative dropped out of the problem. Okay, now sometimes you need to do a little rewriting before you can use the rules that we've been talking about, especially that power rule. So let's think about this first problem, the integral of 4 square root of x dx. Well, the 4 is a constant, so I can move that to the front of my integral. The square root of x can be written as x with an exponent, because right now that's really the basic rule that we're following. So what is the exponent for a square root? Well, it's x to the 1/2 dx. Okay, so now the 4 I'm just going to multiply with my antiderivative, and by using my rule, I'm going to add 1 to the exponent and divide by the new power. So when I add 1 to a half, I get 1/2 or 3/2, and I divide by 3/2 plus c. Now, we don't leave complex fractions, so instead of putting it as x to the 3/2 over 3/2, I need to multiply by the reciprocal of that denominator. So instead, I'm going to write that as 2/3 x to the 3/2. Okay, and then I can still multiply the 2/3 times the 4, giving me a final answer of 8/3 x to the 3/2 plus c. So we had to do a little bit of rewriting before we could actually work the problem. Okay, same thing on this second example here. I've got 2 terms in the numerator, I've got 1 in the denominator. I do not know a quotient rule for antiderivatives. So we're going to rewrite this by splitting this up into 2 different integrals. So we're going to take the first term, the x, divided by square root of x, and then we're going to do the integral of 1 divided by the square root of x. When your denominator is a single term, you can split it this way. Now, those can still be rewritten. So think about your powers. The denominator, the square root of x, is the same thing as x to the 1/2. And on the top, I've got x to the first. And what do you do with your exponents in division? You subtract them. So x over square root of x is the same thing as x to the 1/2. Okay, and then on the second one, I just need to rewrite this and use my negative exponents so that I can have x to a power. So the square root would be an x to the 1/2, but since it's in the denominator, we're going to make this x to the negative 1/2. Now we're ready to integrate. So all we've done so far is rewrite. We have not actually integrated yet. So using our rule, we're going to add 1 to the power. So the x to the 1/2, when I add 1, I get x to the 3/2 divided by 3/2, which we just talked about doing the reciprocal. So I'm going to get 2/3 x to the 3/2. That's the same as it was for the previous problem. Okay, and when I integrate x to the negative 1/2, when I add 1 to a negative 1/2, I get x to the 1/2 divided by 1/2. But again, that part needs to be rewritten. So in my final answer, this part would look like 2x to the 1/2, or you could write it as 2 square root of x. Okay, so final answer, 2/3 x to the 3/2 plus 2x to the 1/2 plus c. Don't forget your constant on all indefinite integrals. Okay, now one more type of example here is when you've got a variable that's in the denominator to start with. So 4 over x squared. The 4 is a constant. Again, I can bring it to the front of my integral. But instead of 1 over x squared, I don't have a power for a quotient rule again. I need to write that as x with an exponent. So I'm going to get it out of the denominator, I'm just going to make the exponent negative. So 4x to the negative 2. Now when we integrate, I'm going to add 1 to the power. So it would be x to the negative 1. Negative 2 plus 1 is negative 1, divided by my new power of negative 1, plus c. And again, as a rewrite, okay, I've got a negative there, so I'm going to put the negative with the 4. Okay, and x to the negative 1 moves your x to the bottom and makes it negative 4 over x plus c. Okay. Look for places where you can use negative or fractional exponents to rewrite so that you have something in the form of x to the n power. Okay, now another thing you're going to see is called a differential equation, which simply means an equation that contains a derivative. We will talk a lot more about differential equations later. We're just going to hit a few basics today. So all of these examples are equations that contain a derivative. Y prime equals dy dx equals f prime of x equals. Could also be a second derivative, but any kind of derivative in an equation is called a differential equation. Okay, so in differential equations, finding the particular solution means we're going to figure out what the c value would be for that equation. In order to do that, you're going to need to know one point that's on the function. It's called an initial condition. So I need to know one point on my function. And in the example given, the one point that's given comes from this statement, f of 1 equals 0. So I know that my graph, or my f of x, is going to go through the point 1, 0. Okay? So my equation is f prime of x equals 1 over x squared. Well, to get rid of a derivative, the inverse operation of derivative is to integrate. But again, just like all equations, whatever you do to one side, you have to do to the other. So the integral of f prime of x would be f of x. The antiderivative of f prime is f of x. Okay, now over here, 1 over x squared, remember, is the same thing as x to the negative 2, which we just integrated and got x to the negative 1 over negative 1, which could be written as negative 1 over x, okay, plus our c value. Now, what we want to do on the particular solution is we want to use that point. We're going to plug in for x and y, and we're going to figure out what c equals so that we can write our equation without the c. Okay, so we know that our y value is 0, our x value was 1, okay, and when I plug those numbers in and solve for c, I'm going to come out with c equals 1. So the solution for this differential equation would be f of x equals negative 1 over x, and then instead of plus c, I'm going to put plus 1 because that's what c equals. So finding the solution to a differential equation, the particular solution, still involves integration, and then you take it one step further and use your point to figure out what the c value is. Okay, last concept for today are some trig integrals, the basic trig integrals. So I want you to think about what your answers were for derivatives of trig. Okay, so the integral of cosine x dx. What function has a derivative that equals cosine? Well, that would give us sine of x. And again, even though it's trig, we still have to put the plus c because there could have been a number added that when we took the derivative, it went to 0. Okay, now you can always check your answers to integration by taking the derivative of the answer you got and see if you end up with the function you started with. Okay, the integral of sine x dx is going to be negative cosine x because the derivative of cosine is negative sine. So in order to fix that, I'm going to have to put a negative in front of that cosine. Okay, the integral of secant squared. Notice that all my integrands are answers to our derivative questions. Well, what function has a derivative of secant squared? And that would be tangent x. Okay, the integral of secant x tangent x. The function that has the derivative that equals secant x tangent x is secant. Okay. The integral of cosecant squared x is negative cotangent x, because the derivative of cotangent is negative cosecant squared. So since I don't have a negative in that integral, I'm going to have to put the negative with the cotangent. Okay, and then our last one would be the integral of cosecant x cotangent x. And the function that gives you that answer as a derivative would be cosecant. However, we're going to need a negative because, again, the derivative of cosecant is really negative cosecant cotangent. So since the negative is not with the integral, you have to put it to the other side of the equation. These are integrals you're going to need to memorize. Let's do a couple examples with our trig integrals. Okay, so integral of 3 cosine x, remember a constant can just move to the front. The integral of cosine, we just said, was sine, so our answer would be 3 sine x plus c. Still putting the plus c because we don't know if we started with a constant or not. Okay, now remember your rules. If there's subtraction, you can still break this up. So the integral of secant squared minus the integral of secant x tangent x. So we can do these two integrals separately and then subtract the answers. Well, the integral of secant squared is tangent. The integral of secant x tangent x is secant x. And we put our plus c on our answer. So tangent x minus secant x plus c. Okay, now in this last one, I want you to pay very close attention to the variable. This does not say dx. This does not say with respect to x. This is a dt. So when we integrate, we are not going to use x for the variable. We're going to use t. Okay, and again, we're going to break this up. So this is the integral of 1 dt minus the integral of cosecant t cotangent t. Okay, so now I'm going to look at my integrals separately and then I'm going to subtract their answers. So since 1 is a constant, remember the rule for a constant was to put your variable back with it. But instead of it being x, it's going to be t minus the integral of cosecant t cotangent t is negative cosecant t. Okay, and then I need my plus c. And since I have t minus negative, I am going to write that as t plus cosecant of t plus c as my final answer. Again, the trig integrals will need to be memorized as well as your basic rules for integration. If you had questions on any of these examples, any steps that I skipped that you're not sure about, put a question mark in your notes and then ask me about them in class.